So I thought today my plan was to continue the little discussion we were having last time about starting with Compusal Python. And then if you want to go over any of the homework, if you had things that were confusing or didn't make sense, we can do that. Why don't I review things first and then you can tell me if there were things that were confusing, we can spend more time on them together. How's that?
Okay.
So what I had in the lecture was to review the Python because we went through that pretty quickly last time. And then the key thing really is how to adding steppables is pretty easy. We don't do that often, although it's important to know how to do it. Cell attributes are important. We talked about that last time. Iterators are important. We talked about that last time. And then the very first thing we did in the first class, we built this cell division simulation, but we didn't really talk about how it worked. So we'll go back and rebuild that cell growth and division simulation, and then we'll discuss how that works a bit. Look at the code, and then we started again at the very end of the last class. We talked a little bit about scientific plots, but we went through that very quickly, and I was going to go over that again, and then we also talked very briefly about tracking fields. I want to do that more carefully. So most of this, in a sense, is review of the things we covered last time, but taking more time. And then if we get through all of that, we have plenty more things to do, but we can discuss anything that you're interested in. So coming back to the Python-based model specification, again, there's this basic concept where we update the cell field and then we do everything else. And then we update the cell field. So they alternate between steps. And as it mentioned the other time, if you really want to, you can change how frequently these things are called. In other words, it's quite easy to call the steppables every 5 Monte Carlo steps or every 10 Monte Carlo steps. It's possible to call them more frequently as well, although it winds up being a little bit more work. And then we had talked about using the Twitted editor. Now, are you using Twitted or using VS Studio Code for your coding? Yeah. Okay, so then everything here will be the same.
Yeah.
The Visual Studio does have extensions that do a lot of the same thing. I have to say I don't use it, so Pedro could show us how to do it. Use the Visual Studio versions. So again, the key thing about Twitted is to remember that you have all of these coding assistants, these simple coding assistants. And the hardest part with that is to remember where they are. And we went through some of them last time. We looked at the markup language ones. And in the Python, in particular, they're useful. Not everything that should be there is there. There are a few things that people want to do that somehow aren't in the Twitted snippets. And if you find something, in other words, if you say, boy, I wanted to paste this in my code and there was no example I could follow in the snippets, let us know, because we can always update the next update. We can add that to the snippets. Sometimes for the ones that aren't used so often, there'll be a typo in the code because nobody noticed it. So we do depend on people telling us what to fix. So coming back again, there's this structure, and actually this has the older syntax here because it doesn't have the on-stop syntax. And I would like to add something which would be a function that was an initializer function, where you could say run this. Start only runs once at the beginning. I would like to have something where you could say run this 100 times or 1,000 times first, to sort of do a relaxation step. But we don't have that. So people who want to do that have to put it in the step function by hand. And so we have always the same structure. There's the init. Inside the init, there's this creator here that anything that goes in the init has to go after that. And then you have the start function that's called once at the beginning of the simulation, the step function that's called once per step in the simulation, and then finish, which happens when the simulation times out, and on stop, which happens when you push that stop button on player. And so often you'll want the same code in finish and stop if you want to have the simulation when it ends output some results, for example. Right. And then again, when we come to the Python code snippets, they're usually just templates, so you will have to edit them. And sometimes they will have multiple options, and so they won't run as written. You'll have to delete or change the code because it'll show you the different possibilities for the particular function, and you may have to select one. In general, it puts in uppercase the things that need to be changed, but it's not always consistent. There are all these here, and they're all used at one time or another. The ones that I use a lot would be cell attributes, extra fields automatic tracking, scientific plots, secretion uptake, visit. And if you're going to write code, if you're writing code for yourself, the steering panels are not so important probably. But if you're going to write code that other people are going to use, this steering panel option allows you to write sliders and this kind of thing to do user interface. It's not the most sophisticated thing in the world, but they're there. And there are a couple of these that that are sort of interesting that I've never used. For example, you can actually make the cell lattice. Suppose you have a cell that's crawling in space. And one way to handle that is to have the boundary conditions be periodic. And then the cell would crawl off one side and come back on the other side. But CompuCell actually does allow you to rebuild the cell lattice, the lattices. So you could say, okay, delete the back half of the lattice and create new lattice in front of my cell. I've never done it, but it does. I know people who've done it. It does work. In general, it's a sort of a funny feature to have. Chemotaxis is useful. The regular extra fields, we don't use that often. Some of these, the SBML solver and MabBoss are for subcellular models. Those are pretty useful. So at some level, almost, and the file manipulation is also pretty useful. So it's worth just taking a little bit of time and walking through all of those menus and getting a sense of what's there. As I mentioned, this concept of steppables, when I teach, I tend to put everything into one file because it's easier to not have to go back and forth between a lot of tabs. But if you want to build modular code, then you should take the functions of your program and break them down so they can be reused. And so the steppables are sort of a natural module that can be reused. So it's possible to have multiple steppables, one that controls cell behavior like cell differentiation, one that controls cell division, one that controls cell death, one that does the data analysis. It's possible to break these up. So cells have a variety of built-in attributes, and we've already seen some of those: cell ID, the identifier of the cell type, the type of the cell. Those every cell has. And then if you've loaded the volume plugin, the cell will have a current volume, a target volume, and a lambda volume. If you've loaded the volume plugin and you're specifying things in Python, then the cell will have a pressure. If you specified it in XML, the cell doesn't have a pressure. That's a bit of a bug in CompuCell. Same thing with surface tension.
Specify this one, because I'm kind of like curious how you define pressure, like how you get the pressure.
I'll come back to that in a minute, because we'll do that exercise. We'll do that. Okay. And then something to remember is when you're referencing cell type, that's an integer. But if you wanted to use types by name, self.type name put in capital letters gives you that link. So instead of saying cell type 1, you could say cell type self dot quote dark, capital D-A-R-K would work. And you can get if you don't remember, you could say self dot get type name by cell, and that'll return the type of the cell. And actually, I think this may have been fixed, so you don't actually have to do that anymore. You could pull the list of all the cell types if you want. I don't think that's something we're going to do very often. Something that we are going to do very often is iterating. And the typical iterators over all cells of a given type. And in that case, you'll use that self.type name option. And all cells, all neighbors of a given cell. So those are the three iterators that we use a lot. If we were using compartmental cells, then there's a special option to iterate over the compartments. And you could also iterate over all pixels or all neighbors of a cell, all boundary pixels and so on. But the one that you'll wind up using the most is for cell and self.cell list by type, and then you list one or more cell types. And that you use quite a bit. Do something to all necrotic cells, do something to all proliferating cells. We do that. Again, there's this problem that if you specify the volume and the surface constraints in XML, then you can't overwrite them in Python. So normally we'll just load the bare volume plugin and surface plugin and then specify the values in Python. And so we did this last time. Plug in the XML plugin named volume, and then in the start function, cell.target volume is 25, so lambda volume is 2. So the other thing that we talked about last time, it's really important concept in CompuCell, is the idea of using dictionaries. The dictionary, every cell comes preloaded with a dictionary. So if we need to add any attribute to the cell, we just give it a key and an assignment. And the nice thing about this is that these dictionary attributes are available across plugins. So that's powerful. I'm sorry, I say cross plugins, cross steppables, because that's powerful. So they're effectively automatically global. And remember that these dictionary attributes can be complex objects themselves. They could be lists, they could be dictionaries, they could even be classes. And sometimes the syntax gets a little bit involved because the variable, the object name will be cell.dict quote key name. And so you'll have something like cell.dict quote key name dot append something or other, for example. So the syntax, but these are cell.dict attribute name is an object, a Python object. And they don't have to be, you can have one dictionary entry, which is a string, another one which is a number, another one of which is a list. It's a general dictionary. As I mentioned, you'd really like the global one to be self.dict, but it isn't. It's called shared underscore steppable underscore VARS, and that's a global dictionary to use. And that's, by the way, sometimes if you've created things like functions inside of a class and or some complex object inside of a class, so inside of what's steppable, for example, those functions will not generally be available inside of other classes. But if you load self into the global dictionary, then you could read self from the global dictionary, and then self.shared steppable vars quote. Suppose I created a function inside of one steppable. If I read out that I do self-shared steppable vars self inside of that function, inside of that class, then inside of another class I can pull that out and use it. The problem is that the referencing looks a little bit confusing to look at, but I can pass things like function definitions between classes using this. I'm not so sure that we'll do that much in this class, but it's possible. We've used the contact energy. This is something that's just a mention. We're not going to, actually, I think it's being added to the wizard. At the moment, we define the contact energy between cells by a big matrix, where we say that the contact energy between cell type A and cell type B is something. In reality, the contact energy is determined by things like how many cadherins are in either cell, how many integrins are in either cell. So there is a function, there is a plugin called Adhesion Flex that allows you to define each cell has so many of each kind of molecule, and then define what the energy between two cells is as a function of the number of molecules on either cell. And in principle, you could translate any J matrix, any adhesion matrix, into this form. In practice, people find it a little confusing to write the math to do it. It's algebra, but it can be a little bit confusing. Why would you want to do this? Well, suppose that I had 20 cell types. If I had 20 cell types, then in principle, I have a 20 by 20 matrix. Now it's only the upper diagonal, but I still have more than 100 numbers I have to specify. And that's not very practical. Whenever I add a new cell type, I have to specify the adhesion with every other cell type, which is also not very convenient, although the wizard helps you with that. And then the other thing is that all cells are the same of a given type. And why could that be a problem? Well, suppose I'm writing a cancer simulation where the adhesivity of the cells is an evolving property of the individual cell. I want to be able to mutate a cell and have it have a different adhesion with its neighbors, which we know happens in cancer. If I use the matrix form, I'd have to create a new cell type every time I create a mutation. Whereas with this, I can simply change the number of molecules in that cell, and that will change the adhesion. So year after year, I say we should always teach adhesion energy or contact energy based on the adhesion flex, and people tend to find it a little bit confusing. So then we wind up going back to the old system. But it's there, and there are examples in the demos folders. There are examples. The manual probably could be more clear, but it's there. We now have, we're working on a wizard page to do that. But you see here, for example, this is how to specify it in the XML. You list the adhesion molecules by name, and then each cell has a default density of each adhesion molecule by type. And then you actually write a formula that says, given the molecules on cell 1 and molecules on cell 2, what is the adhesion energy? And then you can modulate those formulas by a strength of adhesion here. And because it's a contact, you have to specify the distance over which it's summed. And so it's not the easiest. We probably need to make some more examples of what useful sets of contact energies using this. So it wouldn't be a bad exercise, actually. Pedro, you should probably write a little homework exercise for us, which takes a cell adhesion, a cell sorting example, and then redoes it with adhesion flex as a homework problem.
Mm-hmm. That's easy.
But we'll have to give people some solutions too, because it's, as I say, there are a lot of options here, and so people, it's a little confusing sometimes to get into it. Once you have this written down, going from all of this form to get to what the J values would be in the regular contact energy is pretty easy, but going the other way is a little more challenging.
I have a question.
Yeah, please.
So if you count in adhesion flux and contact energy
Right.
simultaneously,
They
so
add.
they add. So like, isn't there like an overlap where we count it problem? Because like your contact energy, I think that can like include part of adhesion energy if this.
Yeah. Absolutely. I mean, so if you're using adhesion flex, you really should not use the contact energy plug. However, the code will not tell you you've made a mistake. You're allowed to do both. So if you had a simulation which used the regular contact energy and it worked, and then you wanted to modulate those energies, say because you wanted the cell adhesion to be evolvable, you could then write a simpler form of the adhesion flex that only changed the energies of some cells. It would be possible to do that. You'd basically say the only cells that had those adhesion molecules were affected by adhesion flex. So yes, but yes, it's a good point. There are a couple of places we're going to find out there are multiple ways of doing the same thing. And in general, if you specify all of them, they add up. So for example, when we do chemical secretion, we will find out there are 3 different ways to say I want my cells to secrete a chemical. And they all operate independently of each other. So if you say secrete in one place and then secrete in another place and secrete in a third place, it'll secrete 3 times. And the reason for that really is historical, that the secretion plugin was written in a rather simplistic way the first time, and then we didn't want to break the old code, So we added a new way of doing it, but we didn't take away the old way. And I suppose it would be better maybe to have it give you a warning, at least saying you're doing the same thing in two different ways. Did you want to mean to do that? But at the moment, we have to live with it. And so I mentioned that in general, if things are specified in XML, you can't overwrite them in Python, but in the Adhesion Flex plugin is a newer plugin, and so you can. So you can specify the global initial values in the XML, and then you can read and overwrite those values on a cell-by-cell basis in the Python. And so that's I wish all of our plugins worked that way, but the Adhesion Flex does. All right. So now I'm going to come back to our little cell proliferation simulation as a way of learning about how the code works. And another thing that Physicell does very nicely that CompuCell doesn't do is that the cell cycle is built into Physicell. It's a concept that exists at Physicell. CompuCell doesn't do that. You have to do it by hand. So there's no pre-existing concept of cell cycle phases or transition between cell cycle. You have to add that. And I would like to actually extend CompuCell to have, say that every cell by default has cell cycle parameters built in. It would be pretty easy. And we actually wrote a package called PhenoCellPy that implements the old version of Physicell's cell cycle, which I don't think anyone has ever used, but it's available if you wanted to try it. You can load the Physicell cell cycle models to CompuCell. For the moment, we're going to be doing these by hand. Of course, we recognize that in reality, the cell cycle is controlled by the internal cell state. It's controlled by a bunch of receptors on the surface of the cell. And so the actual decisions to proliferate, survive, or die are quite complex. And of course, the cell cycle itself is broken up classically into G1, G2, S, M phases, and those have subphases. Again, none of those are pre-built into CompuCell, although it would be easy enough to build say a flag. You could add a dictionary entry, which was a flag which said cell cycle phase, and then change that through a set of rules. So it would only take it only takes a few lines of code to actually add the full cell cycle if you want it, but it's not pre-built. It would be nice to have a module that was pre-built to do that. And we're not going to talk particularly about checkpoints. And so at the moment, all we're going to do is have our cells grow and divide according to rules. We're not going to model the substeps of cell cycle. And so, I mean, if you look at real cell division, it's very complex, and we're not pretty much, well, it's not nobody. There are simulations now that not by CompuCell or Physicell, but there are code bases that will actually simulate the microtubules that chromatin in cells. But of course, those are very expensive. On the other hand, typically, as in Physicell, we'll have something where the amount of space, the amount of nutrient, growth factors, contact signals, internal cell state, possible presence of toxins, all of those things could be integrated to control proliferation to death choices of the cell. And that's a typical thing that we do in CompuCell Python. So the easiest thing that we do would be, again, we can't change the actual volume of a cell directly. We can only change the target volume. And so the easiest way to do that would be to simply say at every time step, we increase the cell target volume by constant. Now that's going to lead to exponential growth of our tissue. Well, cells are going to grow linearly in time. And we know that that's not really true. In reality, cell growth will be limited in some way, but to begin with, that's our simplest hypothesis. And here we see we have to have in the XML plugin name volume. We're not allowed to specify anything else. Then in our start function, we give initial volumes to our cells. Here I've made them all 25. You might want to have some random number added to that to make them a little bit non-uniform. And then in the step function, we go over all cells and we make them grow by, this is 0.01 volume units per time step. And again, CompuCell makes you do all of the units by hand. So you have to write down somewhere 1 Monte Carlo step is 1 minute, 1 voxel is 1 cubic micron, and then you have to figure out what the growth rate should be, for example. So let's build that growth simulation. We've done that already. And I have some of the steps laid out, but we'll create a lattice. You can make it 100, well, 256 by 256 is fine. Here I said 100 by 100. We'll start out with a single cell in the middle. We'll say that it has contact energy and it has the volume, target volume. And then we're going to go into the steppable. And okay, so for plugins, we're going to want contact, volume, local flex, surface, local flex.
So like quick.
Well, let me walk through the steps first. And we're also on this one, I said we're not going to have the growth, the cell division steppable. So maybe we'll do it. We'll follow what I have here. And then we're going to edit the step function to make the growth rate 25 voxels for every 500 Monte Carlo steps. Having it grow by 1 every time step is too fast. And then we also would like to plot the cell volume per time. And we want to do that. And then we're going to play with the surface steppable. I mean, the surface plug-in a little bit, which we've already did 2 weeks ago. And then when you use the surface constraint, you're going to find you're going to have to keep updating the target surface in line with the target volume, or things get messed up. So first thing we're going to do is create a new simulation. And I realize that some of these are not completely consistent. I said 100 by 100 before, now it's 200 by 200. 256 by 256 is fine. I think you could tell at some level, the older the slide, the smaller the simulation. In other words, these days 256 by 256 runs very fast. 10 years ago, 100 by 100 made more sense because it ran a little fast. So 256 by 256.
You want to change the pixel copy range to 3?
I would make it 3. I normally do. And we'll use blob initializer. And then we only need 1 cell type for the moment. And then we'll use contact, growth steppable, volume local flex, and surface local flex. And we'll skip everything else. And then when we go back to the, you got your code. So now go to the XML first. And make the radius and the width 5, so you only get one cell to begin.
It has.
Okay, and then in the growth steppable, you should see the start function. It should probably say cell target volume is 25, cell lambda volume is probably 2 by default.
Yeah, so I change it to 3. Right?
Yeah, 2 is a little soft, but we make it 3 is fine. And again, in reality, if we were building a real simulation, we'd make these rules more complicated. But to begin with, we're just learning how to do it in a simplest possible way. And then in the step function, the one thing is, I think it says cell dot target volume plus equals 1, right?
Mm.
That's way too fast. So make it something like 25 over 500. That would have the cells double in volume every 500 steps. Again, in reality, that growth rate will be made to depend on growth factors. It would depend on pressure in the system and other things. But for now, we're just having constant growth. Okay, so now why don't you try running that, see if it runs.
Yes. I think I need to restart it.
Did it crash?
Oh, it didn't crash actually, it's just too fast. This is pretty simple, so it's run very fast.
Okay.
You can see like it's running.
Yeah, that looks, should be okay. Let's see.
And I just.
Yeah, that's fine. So let's let it run. The cell should just grow, not do anything to
Oh.
grow. That looks fine.
Yeah.
That's right. Now here I've said, let's put in some plot windows to display the volume, pressure, and surface tension. And then, but I haven't actually done the plots yet. So let's see. Hold on a second. I'm going to have to look at I changed the order here a little bit. Let me see if I can find that. Okay, so I'm going to jump down to here for a second. Let's talk about how to do a plot. Okay. So for plotting, CompuCell basically has line plots and histograms are the two kinds of plots that it has built in. And again, when we talked about this very briefly at the end of class last time, but let's just go over it again. To do a plot, we have to first create a window to display the plot, and that goes in the start function. Then you have to define the data series that you put into each window. It also goes in the start function. And then in the step function, we actually add the data points to the series. And Twit has the code snippets, although we'll have to edit them by hand. It has the setup function, which goes, it says in the start function. It has, it calls add data points is in the step function. And the setup function includes both the window generation and the time and the data series generation. And there are times when you do want to be able to erase plots. Something has happened and you want to erase what you had and replot. That happens pretty often. And it's also possible to save the image of the plot as a PNG or save a data file of the plot. Now, in general, the things that are going to be pasted in here are not going to be quite what you need. So you're always going to have to hand edit the code a little bit. So the general function, and let's do that, go into the start function, not inside of a loop. It should be outside of a loop. And then add the setup for the scientific plot. Yeah, you don't want it to be inside that 4-cell loop because you don't want it to be done multiple times. You want it done once. Okay, and so it'll paste this code in, and self.plotWin is a handle, and you could give this different names. You could call this self.myplot or self.window1, but each plot window handle has to be unique. So if you're going to want to have 3 different windows with plots in them, you'd have self.plotwin1, self.plotwin2, self.plotwin3. You have to remember the names. And then there's a function, add new plot window. And then every plot window has a title. And those titles have to be unique. I'm not quite sure why that is, but they do. Y-axis title usually is time, but could be something else. And it doesn't have to be labeled in Monte Carlo steps. We could convert that. And then the Y-axis label could, sometimes we know what it is, sometimes just variables. And then you can have the X and the Y axes be linear or logarithmic. And you can have a grid or no grid. And you can also have a variety of other options. Now, the people tend to be, with Python, people tend to be used to matplotlib, but this is not matplotlib. It's a different package. And I'm trying to remember why we didn't use matplotlib. As I recall, there may have been a licensing issue. In any case, we didn't. This plotting package isn't bad. It doesn't have quite as many features as matplotlib. And the syntax is slightly different, which is not always very good, so it's a bit confusing. Within this plot window, once we have the plot window created, we need to add a data series, and we give each data series a name. And then we have a variety of options, lines or dots, color, size of the line, and so on. We can have multiple data series. We can have multiple plot windows. We can have multiple data series inside of each plot window. Something that you do sometimes use, by default, the plot windows are auto-scaled. By default, the plot windows are auto-scaled, but you can also have fixed. If you don't want auto-scaling, you can fix the X and Y ranges. And the manual talks about all of those possibilities. And Pedro makes a comment that you can use matplotlib. You can load matplotlib as a library and use it inside of CompuCell, but it doesn't work very well inside of Player. I guess matplotlib will wind up visualizing to the console. So if you were going to use the Python, the Jupyter Notebook deployment of of CompuCell where you don't have player, then you could use matplotlib, for example. And then inside of each, inside the step function, we have to add, sorry. Oh, there's just here, you can also have there's a legend, configure options legend. True will label the time series, the series of your plot, if you want. That's one we use pretty often. I think it gives you at least some of the options when it pastes in the code.
Yeah, I think like other than the config options, all of the remaining options are listed. Like when you just paste them.
Right, but you're going to have to get rid of some of them because some of them are incompatible with each other, right? You can't have it both be linear. X scale type is linear, X scale type is log. You can't have both, so you have to pick one.
Oh yeah, they would just give like an example.
Right. Yeah. So you have to clean that up. And then in the step function, what I had here was I created a volume time series and a surface area time series. And so then in the step function, we add the data point to the volume time series, MCS comma cell volume, MCS comma cell surface. So why don't you actually do that? So let's create a plot, which is the average volume and surface. X-axis Monte Carlo steps, Y-axis we could just call variables, linear, both X and Y, and then to add a data series, mvol, msurface. I said lines and dots. I probably would make them both lines or both dots, both the same size. And then in the step function, go in, you can use the twidit inside of the step function, add mvol, MCS cell volume, MCS surface, and let's make sure that runs. And one thing is you do have to remember that the handle for the plot window and also the name of the series, because those have to match exactly. So did that work? Okay, so does it tell you what the line was that had the error?
Yeah, it's an error, so it's like growth that.
Right, but it should give you the line number where no, it probably doesn't mean that. Well, let's see what the line number was. So you have to scroll down to the bottom. And we'll tell you what line error, 47, okay. 47.
Yeah,
okay, so it's because you don't have the configuration set up inside of okay, I see the problem. So scroll up a little bit. So you have two classes here. You have a constraint initializer steppable, and you have the growth steppable. Okay. The handles that you've created in the start function in one class are not available in another class.
Oh,
so what you'd want to do is copy lines 10 through 14.
Oh.
You don't need the start one. You don't need
okay.
Right. You don't, and then you're gonna have to paste them into the other. Well, don't cut and paste them because you're
it's okay. I can just adjust
no, undo, because you need
okay.
because you're gonna need that. You're gonna need that. You're gonna need that loop. Now, there you go. So let's just copy it because you'll need line 10 too. You'll need line 10. Because growth steppable doesn't have a start function built into it. Yeah, there you go.
Oh, so like growth that class didn't have a start.
It's not required.
Oh. But if we're going to like create a plot, so we have to,
If you're gonna do plots there, you need to have a start function to
Okay.
do it.
okay, I see.
Okay, so now you can go back up and get rid of those duplicated lines in the other. So now you can get rid of lines 11 through 17.
Oh, okay.
So that should work. See if that runs. There you go.
Oh, yeah. Oh,
That looks good.
that's- Yeah, always.
Okay. And if you want to if you want to have it display the series and use this, add this option, config options legend true when you create the window.
Oh, comfortable.
That's a case where if we were in VS Code, it would could do command completion. It would be a little easier, probably. But let's make sure that that runs. Right. Once you've done it once or twice, it's easy, but typo.
Just checking. Oh, the truest inside the dictionary, right? Equals double. Wait, it's.
Let's see, what's the error? Sorry, what's the error?
Just the PSI.
What's
that-
the error is in that? Okay, so I scroll back.
Oh, it's a code, I'm
It's not,
sorry.
it's not an equal sign.
Yeah, it's a code. So,
One of these great Python.
sometimes this is.
Did that work? Now it's displaying. Okay, good. Yeah, that should probably, by default, that should probably be turned on. All right, so now you've got that. So now let's jump back to where we were so we can see about what we were doing. So that we ran this simulation and we can now see the surface and area as they change. And now let's turn on the surface constraint. So let's cell dot target surface 20, cell dot lambda surface 3 in the initializer. And now let's run it and see what happens. And you might want to think about what happens before you run it. Is this going to work? It's going to, well, it shouldn't crash, but is it going to do something that makes sense? What's going to happen?
I think like in previous simulations, we observed as the cell grows bigger and like the surface of it is less crumpled. And I think like if we add these two ourselves, I think the cells are still like going to be crumpled, even though like they're, like the volume is increasing.
Okay, great. So let's see what happens. Let's try running it. So what happened? Actually, are we running the new simulation? Let's see.
think, yes, because
Is the surface constraint loaded? Let's see. No,
I
it
can
is,
try
no,
it.
the surface plugin is loaded, that's fine.
Mhm.
Target surface is 20, lambda surface, no, because you've got lambda
Oh,
volume.
right, okay.
If lambda surface isn't specified, it's 0, so it's not doing anything. There we go. Now try. There we go.
Huh? Oh, it's more it's not, I said it's more crumpled, but you're adding the.
This is like taking a
Oh, yeah,
tire and the target volume is like pushing air into the tire.
yeah,
But the size of the membrane, which is target surface, isn't going up. So you're making it stiffer and stiffer and stiffer, but it'll stop growing because it's constrained by the surface. Yeah, right, right,
okay,
right.
that's.
So you'll get that. Good. So now we come back to this shape function that we had before, shape factor. And this is something that the Morpheus language does better than CompuSol. Actually, Pedro, did they implement can we specify the surface in terms of the target volume now in CompuSol?
Not to my knowledge. Maybe I didn't read the full updates for the last version.
Because we've been wanting to have that available for a long time. Because really normally what you want is for the surface to track the volume.
Mm.
Now in 2 dimensions, what you want is, again, this function looks sort of complicated, but if it's in 2 dimensions, it would be that the surface goes like the volume to the 1/2. That's all. And so what you would do is you would set the target surface to be the square root of the volume multiplied by some number, right? And so a pretty reasonable one to start with would be to say that in the step function, when you add to your target volume, you update the target surface to be, here I say 2 times pi times square root of cell dot target volume. You may need to use np dot pi. I don't remember if pi is predefined in CompuSol or not.
Yeah,
So
I think it's by default importing the.
NumPy is imported as np usually.
Yeah,
So np dot pi will work. And so now you can have the cell stay with essentially the same rigidity or the same shape. And so let's try running that.
so.
So how does that look?
Um, the, it's the,
It's still getting a little square, isn't it?
yeah,
Are we sure we're updating the target volume, right? Target surface? Let's see, where is the target surface? Oh, but you have that in the start function. You need to put that in the step
Oh.
function. So putting it in the start function is fine, but you also would need to put it in the step function.
So let me copy this. Okay, sometimes it's kind of like confused about me. So did you put it?
Yeah, the start function only does it once. Okay. It's a little crumpled. Now look at the plot on the bottom. So you could see the actual volume is going up linearly. Before the volume was getting pulled down because it was being constrained by the surface. Now the volume is keeping going up, the surface is going up like the square root of the volume. The cell is a little bit rough, wrinkly. So let's try making the target, let's try moving up and down from that target. So let's try in the step function. If we go back to the step function, let's multiply that by 0.75.
Just change the target surface.
Right, just in front of the whole thing, make 0.75 times the whole thing. Now that'll be a little less surface area, and let's see what that looks like. Maybe we had a little too much surface for that one.
It's less crumpled.
It's a little crumpled. That's not bad. That's pretty close to what I would say a normal cell should look like. Sometimes cells really are crumpled. So in that case, okay, and let's try going the other way. Let's make it times 1.5 instead of 0.75. Now the cell's really falling, crumply surface. So 1.5 is too big. 0.75 looks like it's about right, I'd say. So let's go back to 0.75 and we'll work with that. Again, it would be nice if all of these things were defaulted to instead of having to make you do it, but once you know how to do it, it's not so bad. Okay. Okay, so now we're going to do cell division. Now, in reality, cell division takes a lot of time and it's very complicated. But in both Physicell and CompuCell, we just say the cell has divided, as if that happens at an instant. And we have some rule for cell division. And in CompuCell, the simplest rule we have is to say that if the cell volume gets to be bigger than, or twice its original volume, then we divide it. That's not a very good approximation to the biology, but we can put in fancier rules later. Once we have a place for the rule, we can substitute it with a fancier rule. So this is really just to show you how to use the rule, not really so much to, okay. So now the thing when you do cell division is that we start out with one cell and we wind up with two cells. So you have to create a new cell. And we're going to call the original cell the parent cell and the new cell the daughter cell. And we have a bunch of decisions we have to make. In particular, when we divide the cell, are we going to divide it equally or unequally? And then are we going to have the division be always along a fixed direction, along a particular axis relative to the length, the long or short axis of the cell, or randomly? And those three different things are supported. We can specify a fixed plane of division. We can specify dividing along the long axis or the short axis of the cell, or random orientation division. And then we also have to say how are the attributes of the parent cell inherited by the child cell. Now, since we don't have a concept of cell cycle built in, whether the cell, the daughter cell's arrest or not is something we'd have to put in by hand. That's not given to us. There are a lot of possibilities. So CompuCell has something called the mitosis steppable to do that. And it takes care of dividing cells. And we are going to have to handle things like inheritance and cell type by hand when we do that. Cell division is typically triggered by some condition. That condition could be, again, we're going to use the volume of the cell to trigger it, but in reality, we'd have perhaps some cyclins that would trigger the division. Or we'd have some timer the way you do in Physicell. Now, one thing that we have to do in CompuCell, because it's Python, is that when we go through the list of cells, we don't do the division while we're going through the list, because that's not allowed in Python. So what we'll do is we'll go through all the cells. We put all the cells we want to have divide into a list, and then we iterate over that list and divide the cells. So we have to do it in 2 steps. First, we identify the cells that are going to divide, and then we do the division in 2 steps. And that's because we're not in Python, you're not allowed to change the list you're iterating over. And so if we divide the cells while we're iterating over the cell list, we're changing the list of cells. We're not allowed to do that. Okay. So there is a steppable class called mitosis steppable. And if we paste the mitosis steppable in, you'll see that it has 3 sections to it. It has a section where we go cells to divide equals empty list, for cell and self.cell list, a condition if volume equals 50, this is a very simple condition, cells to divide append cell. So this first part of the mitosis steppable looks at all the cells and says which ones are going to divide. Now we could have a more elaborate rule. If cyclin A bigger than something and cyclin B less than something else, then divide the cell. We could have a complicated rule. Then there's a second part where we go through the list of cells we've just built that are going to divide, and we have them divide. And we have self.divide cell random orientation of cell. That divides the cell along a random orientation. We could have a fixed orientation, major axis, or minor axis. Those are our 4 options. And then the last thing that we have to do is we have to update the attributes of the cells. And the first thing we're going to do is change the attribute of the parent cell. And we almost always are going to set self.parent cell target volume divide equals 2. We're going to give it half of the volume that we had before. And if we have a target surface, we'd have to change it here too. We'd say self.parent cell target surface equals the same function that we just wrote down before. Then there's this very powerful function, which is self.clone parent to child. And that says that the new cell that we just created has the same properties as the parent. And we could, if we wanted to, restrict copying only certain attributes, but in general, we copy everything. Simple. And one thing that is nice about this copy function, it's a deep copy, is that even things that we added to the cell, like dictionaries, are copied. We don't have to copy the dictionaries by hand. And then the default, which is sort of a bad choice of default, is that it also shows you that maybe the parent changes type or the daughter changes type after the division. The problem with that as a default code is if you only have one cell type, it's going to crash because it assumes there are 2 cell types. Okay. So again, the steps are, we create a list for cells to divide. We go through all the cells, check whatever the division rules are. We add our cells to the list. We then go through all the cells that are dividing, divide them, whether randomly, fixed, or major minor orientation. Then we update the attributes of the cells and clone the attributes to the child cell, and then do any kind of type updating or other updating that we need after that. So there are 3 steps. Pick the cells to divide, divide the cells, update the attributes. Okay, so let's add the mitosis steppable. And we do that by going over to the, select your, click in the click in the navigation pane on the Python step, on the steppable Python file and say add steppable. Right click. So it's a right click. It's not a pull down. There is actually a pull down menu for add steppable too. But so go over here where it says Python.
Here?
Yeah, that's
Okay.
fine, yeah. Okay, and now right click and say, what I said. Okay, now I guess you have to go to the top level, so,
This one?
yeah.
Okay.
Does it have ads? Where's ads? Where's add steppable?
Mhm.
Why is it not there? All right. Add steppable.
Oh.
Yeah, okay, add step. It got it. All right. And so now we need to give the steppable a name. Yeah.
So,
Call it cell division or something. Yeah, that's fine. Mitosis is fine. We don't need any of the other. We don't need any. Those are fine. Okay. And so now let's put it inside of the same file. So it's put a new class into the same file. We could create a separate file to put that in if we wanted to break it off. Okay. And now we want to go through this and look at the, that's how we did it. And again, we have to remember that if we need to pass information between steppables, we have to use this self-steppable shared variables. We could global things, but globaling is a pain in Python. I don't know if you use global variables in Python, but so if you put parameters at the very beginning of your code, all the way at the top, those are available to all the classes, but they can't be changed. If you try to change the value, you'll get an error. So you can specify parameters that way, but not variables.
okay.
If you use this steppable shared variables, then it's available. And that one is not, I don't think, in the code snippets. It should be in the code snippets, but it's not. So I would just copy this text, put it in a comment somewhere in your code, so that when you need it, you can look it up.
Okay.
So I just literally put percent self.steppable underscore shared underscore variables bracket variable. And then just that way you remember it so that you don't have to look it up.
So if I have a question, so if I define a variable and I call this method by turning it to like a globalized variable.
Yeah.
And if I change the variable under the function that I define it,
It changes it everywhere.
oh,
So this is like creating a global, is effectively the same as creating a global variable. And then, but if you create a global variable, you have to create a global, and then at the beginning of each class, you have to say global, and then list all your variables. And so you could certainly do things that way, but it's a little inconvenient, because then if you add a global to one place and you forget to put it in the other ones, it's not available. So
yeah, it's not looking very good.
right. Whereas this way it's automatically available everywhere.
Um,
So again, Python really likes dictionaries.
mhm.
So it's
Kind of like a seed pod.
yeah.
I don't know if it counts. But, okay, I was just remembering.
So
You can go ahead.
that's okay while you're typing. I just want to double check something. I want to make sure I spelled that right. Okay, there's a typo in that slide. Pedro, are you there?
I'm here.
Is it shared steppable variables, or is it steppable shared variables?
Uh, I can check that on GitHub. I don't know from
Because my slide has, I'm pretty sure shared underscore steppable underscore VARS is correct. But the slide actually had the syntax reversed.
I'll
Let
check
me-
here.
I could just do it, and I've got Twit running, so I can do it in Twit.
Shared steppables, shared steppable vars as it is in your slide.
Okay, good. So then I have to fix the other slide because the other slide has it backwards. It's not a huge thing, but I don't want to have the wrong syntax in this.
Like the first page that we map this.
There.
Because I also have a question about the like cells type during mitosis.
Yeah.
So since like cell or does cell not allow like two same cells but like with the same type attribute? Because like why do we assign the parent cell and child cells two two types?
Oh, so that's why I'm saying that was just to illustrate that you could have differentiation happen on division. But as I said, I think it was a mistake to have that be the default. So I would go, let me come back to. So so let's go through the code. We pasted in the default code. So let's make the cells divide when they get to cell volume greater than 50, okay? And then we'll divide along random orientation, that's fine. We'll set self.parent cell target volume divide equals 2. And then copy that line that you had before, which is where you set the target surface. So set self.parent cell dot target surface equals whatever the function of parent cell target volume was before. Can you do that? So you go back to where you had the growth in the growth steppable, where you updated the target surface. Yeah, copy that line. Just the target surface update line. Okay, now copy that line down after self.parent cell ... Okay. Except now you're going to have to, instead of making it cell, you're going to have to make it parent cell.
That'd be like self-parent cell.
Self.parent cell on both sides.
So there's okay.
Okay.
I'm going to get that.
Okay, and then we've got self-clone parent to child. That's okay. And now I think, does your default code have a type change in it?
Mm-hmm.
So just comment that out or delete those lines. You're not using those. Those were just to show you that you could change the cell type. They should have been hidden. I mean, they should have been commented because they crashed the simulation if you only once. Okay, so now save it, and this should now run. Now you're gonna get an exponentially growing number of cells because,
But it's not. Like, oh, it's not like 50 yet, maybe?
well, we can see it's what's the, no, it's just 50. Let's look at the, look here. So something happened, so let's see what happened. Let's see. If cell volume greater than 50, cells to the right, cell to the right. That should be right. So parent, so it's fine. Can you just hit save and let's run it again? Because I don't know why. That should be the.
So,
Why is it not dividing? Huh,
okay.
all right, so let's look at the. I wonder when we added the stepable, let's look at the code. Let's look at the main Python script. It did register it. Huh. Why is that not working? It should.
Do we go back to this?
Okay, there must be something obvious that I'm missing.
But it's like almost like all over the phone.
Right, well, it's not calling the,
This class.
I don't think it's ever, let's just put a print statement in the step function.
Okay. Just add print for all of the functions.
Yeah, just print in mitosis step.
Oh, okay. So we just run it quick.
Fine. Okay, so now let's run that. So did you save it?
Yeah.
Okay, and now hit pause. And now we need to find the,
Right.
no, the Python, where's the Python window, the raw Python, the actual, the console, where's the Python console?
I think this is, but I'm not sure if I. Oh, I have like more. Yeah.
There it is.
Yeah.
So that's where it's supposed to, you're supposed to be able to redirect prints to there, but it doesn't work for some reason. So it's never printing, so it's never calling that stepable.
So that means like it didn't call this class.
So somehow the register. That's mitosis stepable. Registration is not. Why not?
Also, can I go downstairs to get some to?
Oh, sorry, sure.
I'm sorry.
I'll tell you what, would you be willing to go on to Zoom and then maybe Pedro?
Okay.
I'm not sure what's,
Yeah.
we added this mitosis stepable. It looks right to me, but the mitosis stepable is not getting called. When you do an add stepable, it should automatically register the stepable.
Yeah.
So she runs the code, it doesn't generate an error, but the mitosis stepable is never invoked.
All right.
And
You can take a look.
Yeah, that's what I figured. If you can log into the Zoom, then she can screen share it and we can.
Just a second.
But I'm just looking at my code to see why. Very odd. I don't think.
Check if I was in the correct name. Oh, yeah. Mm,
Because I normally create the mitosis stepable when I do the initial
So I'm sending a request for sharing this one.
if you just okay, you got it. You'll have to ask for permission to screen share, and then I'll give it to you. Okay, good. Okay, there you go. So you should be able to screen share now.
Oops. I think it's um, let me change this.
Actually, are you screen sharing?
I think I'm not scared.
You should. Okay, why don't you share now?
Oh, okay. Just a second.
There we go. So we have mitosis stepable, definite, mitosis stepable base. Let's scroll down.
Actually, I just
I think the problem is that you didn't save the other Python file.
Oh, did you not hit save all?
Yeah.
hit save.
No, you always hit the save all. Always hit the one with two. Always hit this one here. That
Okay.
one. Okay, now try. Now try.
Okay.
Well, it crashed, but let's see why it crashed.
Um,
Go back to here. No. Okay,
This is like no.
so let's see. So go back. Mitosis stepable is no divide, so there's no object there, and so it's a one. Okay.
Yeah, but it's like. So do you wanna like,
No, that should be fine.
or
Let's see.
actually,
Did it not load?
I don't think because I just replaced this file with that one.
You changed something?
It's just for like.
Oh, no, oh, no, you can't change, you can't touch that. If you change that, it's definitely not gonna work. Did you restart it? I don't think it restarted.
Yeah, I restarted and now it reports error.
Okay, hold on a sec. So what's the error?
This is like, it's not defined. We go input.
Oh, because, so, no, so go back to,
Oh, start over base, sorry.
yeah. Yeah, the inheritance is from stepable base. Yeah.
That's still wrong. Undo until you have the correct.
But it's
No, that
now
works.
working.
That worked.
This
Yeah.
works?
Yeah.
Yeah,
What do you think is wrong, Pedro?
yeah, what do you
Well, I
think?
never seen mitosis tappable base as a argument
Yeah.
for the class.
So that's why I changed to, like, I keep the, like, class identical with the two previous ones.
No, it has to be, whatever it gave you is what is correct. Don't ever,
Okay.
it knows the correct argument for, let me see what it is, and let's see.
What happens after we didn't like notice it divide, so I just changed that, but I think like the.
Yeah, no, mitosis stepable base is correct.
Okay, so I
Ah,
think
all right.
the root cause is still, is because they didn't save the.
That's right, you have to,
Yeah.
well, it's not the stepable that you didn't save. So go back to, that's why you always have to save everything.
Okay.
This main Python script here, you have to, when you create a new stepable, it says from new simulation, import mitosis stepables, compusol setup register stepable. If you don't have that line, number 21, then the steppable is not executed. So, okay, great. Okay, if you want to take a break now, go ahead. Go get a bite to eat. I used to, when I had more students, I used to bring cookies for days like this, but I didn't think to bring cookies today. Well, at least they have that little cafeteria thing open now. For a long time, that was closed. For 5 years after COVID, that was not operating. So,
Like
Okay.
a few.
okay. All right, thank you, Pedro. Yeah, no, you're right. The thing was I always just say, remember to hit save all, but people have a tendency not to use that button. And because I do that automatically when I do things, I forget that sometimes people forget to do that. How are you doing, Pedro, while we're waiting?
I'm good, James. I'm reading your reviews, your good reviews of the paper.
Well,
Slowly.
I think that what you had was good, but there were a couple of places where you could be a little clearer.
Mhm.
And so I was trying to anticipate what a reviewer might think about, and that's why I put those there.
Yeah. Aditya said he might join back the RU thing.
Oh, that would be nice.
Yeah. I think what he did with the likelihood profiles, where you give the model as an argument and it returns all the likelihood profiles for all parameters. That's a powerful tool. We could make something more serious out of it, um GitHub um pull request to
Yeah,
the Tellurium thing, and maybe in the next textbook update by Herbert include that in it as well.
that would be nice. That would be powerful. I think that's a great idea.
We also found a GitHub repository with standardized models for diabetes control.
Oh,
It has a collection of mechanistic models
yeah.
and neural networks as well. And they all work the same way, inputs and outputs. So you can with one command, you choose the model, you train the model. The data set is already there as well. They have data sets from multiple sources. All the data sets are standardized as well.
You mean experimental data sets?
Yeah, yeah,
So not just
real
synthetic
patient.
data, but real
No,
patients. Oh, that's
real
pretty neat.
patients. Yeah,
You can see how well the experimental data, how well you could fit the simulations to the experimental data.
yeah. And there are built-in commands for evaluating the models as well. It returns different metrics for accuracy and prediction, not prediction cones, but because it doesn't do ensemble prediction, but it does like for each point of the
Right.
data, it has a corresponding trajectory to it,
Right.
which is
Sure,
very nice.
because the actual time series doesn't match the prediction. So at each new time point, you can predict forward from there. You'll get a different prediction.
Yeah,
Yeah.
exactly.
So it has rebasing.
Yeah.
Yeah.
So what a gold mine. And ChatGPT actually pointed me
Found
to this repository.
who wrote it?
It's a Norwegian PhD student, Miriam. It's her name.
Was that Osmond Flowbox Group or somebody else?
Let me find it.
Not that it matters that much, but it sounds like that we know a guy who does that kind of modeling. And I just wondered if it was his. Boy, I'm gonna have to put my coat on. It's cold in this seminar.
So her paper about this GitHub repository 2024. There is so Miriam Wolf is the main author, and then
Yeah.
Sam Royston, Anders Lyngvi Faulkner, Hans Georg Schaffen, Martin Steinert, and Rune Volden.
No, I don't know. What university?
This is
Yeah, it doesn't matter.
Sam Royston is the CEO of Replica Health.
Okay, so it's a company, not a university.
No, but she I think the main author I think is a PhD in a Norwegian university, NTNU.
No. Norwegian Technical University, yeah. Okay. All right.
Yes.
Okay,
Science and
great.
technology, yes.
Great. Well, we need somebody to do a company around CompuCell, I'll tell you. Now's the time to do it. Somebody where entrepreneurial would be the time to do it. Okay, well, we're going to get back to class now. But thank you,
Right.
thank you, Pedro. That's great. Okay. Yeah. Yes. So just in fact, if you only save part of the it's not very prominent, but when you make a change, okay, when you make a change to one file, you notice it's red.
It's all saved.
Unsaved, yeah. So we should have, if I'd been looking for it, I should have seen that this one was unsaved. This would have been unsaved. That's why it's been so.
Yeah, so it means like the previous version didn't include this round execution of this.
right,
algorithm,
that's
so-
right.
Okay.
Right.
Got it.
Again, maybe the default should be having the save all on the left so that that's the first one people use.
I think it's short cut.
I always use the save all always. And so I forget that people don't always do that. And then, so I make plenty of mistakes, but I'm most familiar with the mistakes I make. And so, all right. So now let's try running that and just see what you get when you run it.
It's just really long. Maybe you wait. Like, oh. Let's just tracking oneself.
So it's running a little slow, but the main reason it's running slow here is because of the plot. I think we're actually plotting the volumes of all of the cells. Let's see, when you do the plot function, when you add the data point, is that inside the loop?
It's above.
It is.
Yeah. Oh, so you mean like cancel the?
No, it's okay. But you're adding Okay, it's fine. Just let's watch the simulation for another minute or two.
Okay. No.
Where's the, okay. So,
But I think it looks pretty correct.
yeah, it's doing what you want.
Mm.
Now, so it's pretty, and the one thing that I wanted, it'll take a little while because we're having it grow fairly slowly.
Mhm.
Is we have exponential growth here. It's dividing. Every cell is growing at the same rate, and it divides.
Oh, you mean like for
Right.
the population number?
Right.
Okay.
So what'll happen at a certain point is it's going to fill all the space,
Mhm.
and then the pressure is going to keep going up because the target volume is going to keep trying to go up. But now we have the actual we have the volume in surface rather than the target volume, and we're dividing on the actual volume in this one, in our cells to divide. We're checking the actual volume if cell volume is greater than 50.
Mhm.
So in that case, once the cells fill all of the space, they're not going to divide anymore
Okay.
because there won't be their actual volume won't go up.
Yep.
And so this model will desynchronize a little bit, and it has some pressure, it has some kind of contact or pressure limitation, because if the volume can't increase, then it doesn't divide. On the other hand, the target volume will keep going up.
Mhm.
And so now let's do the pressure. And so let's see, I'm sorry, these are slightly out of order for the sequence that I had. So now let's do the pressure. So the cells actually have the pressure built into them. So cell dot pressure exists. And it's defined as the pressure is the derivative of the volume energy with respect to the volume, which is -2 times lambda volume V target minus V. And it's defined a little bit backwards. If the actual volume is bigger than the target volume, the pressure is positive. And so, and the same for the surface tension, -2 lambda surface times surface minus S. Now, we're adjusting the actual surface to be tracking the target surface. I mean, this should be we're adjusting the target surface to track the target volume. That's actually going to get strange when the system gets locked up. We should probably have the target surface track the actual volume rather than the target volume.
Mhm.
Normally, if the system is not compressed, the actual volume and the target volume are close to each other. In this system, once there's no room to grow anymore, the target volume will keep going up. The actual volume will stay fixed. And so then if you make target surface depend on the target volume instead of the actual volume, the target surface will also keep going up. And the cells will crumple up.
The target surface. Oh, because we didn't update the target surface.
We're updating the target surface,
Yeah, we are.
but we're updating the target surface based on the target volume, right? Not on the
Mhm.
actual volume.
Yeah, so that means like the target volume and target surface are updating together, and the shape factor is calculated by these two.
Right. But the shape factor is given by the actual volume and the actual surface.
Actual, but like in your slide, it says target,
Right, so,
or they're separate.
right, because we cannot control
Mm.
the actual surface and the actual volume.
Oh,
We can only control the target surface and the target volume.
s-
But
okay.
when you update the target surface, you have to ask, should I update the target surface based on the actual volume or the target volume? Normally, it doesn't make any difference. But when you run out of space, is the simulation still running?
Oh, I stopped it.
Oh,
I
no.
ended.
Oh, don't. That's too bad.
Oh,
So let's make the volume grow faster so we don't have to wait so long.
okay.
So
Mm,
make that multiplied by 5. Say. Okay.
That's not about that.
And let's see what happens. Let's watch the
Okay.
the simulation run. Okay, so now it's going to run out of space.
Mhm.
And you'll see something strange happen if you look at the plot of the volume of surface.
Because like
No,
they're not.
look at the time.
Oh, this one. Oh. Mm,
Because the target surface will keep going up. Well, we haven't run into we still have room, so it
mhm.
hasn't.
Yeah.
But you can see it's getting compressed in the middle because the volume is growing too fast.
Yeah, I think like through this, the updating is not evenly
Well,
happening on this.
no, it is it is even, but the growth rate is too fast for mechanical relaxation of the tumor. And that happens in real tumors. The pressure inside the middle of a tumor can be very high. As the cells divide very quickly, they can create pressure in the middle. And so that's why I normally slow the growth down so it behaves better. But for the thing we're doing here, we want to be able to see the effect of having the volume constraint. What you'll see what you'll see when it stop. Oh, there we go.
It's just kind of slow.
Yeah, well, when you get more cells,
Mhm.
the thing that's slow here actually is this plot. Because it's plotting, there's a point for every cell, so it's plotting a lot of points there. And it redraws the whole plot every time. So when you have a lot of points in the plot, it's a slow update. But the next step or two, it will.
Yeah.
Okay. Fine. So now you may not see it for a while. You'll see that you'll see that the target volume will keep going up. The target surface will keep going up because it's slave to the target volume.
Mhm.
And the actual volume will not keep going up. And you'll see the cells are getting all crumpled up. They're getting
Mhm.
too much surface compared to volume. All right. So there are a couple of things to do here. In the first case, we actually have the pressure available to us. We could calculate the pressure. The pressure is -2 lambda volume times cell dot volume minus cell dot target volume minus cell dot volume. Or we could just use cell dot pressure. That exists. That's an attribute.
Mhm.
And there's also a cell membrane tension, and I have to look up what the name of that one is. That's in the directory. So the other thing is something to do if you want things to, you can have the steppables execute every 10 Monte Carlo steps or every 100 Monte Carlo steps. If you look at the top of your steppable, in the init,
Mhm.
it says self dot comma frequency equals 1. If you make that 5, then it only executes every 5 time steps or 10. But the other way to do it is just at the beginning of the steppable to put in if not MCS percent 10 colon, that'll execute every 10 Monte Carlo steps.
Mm. You like initialize the or
In the
like,
step, inside the step function.
oh,
So if you change the frequency of the init, then that's changing the whole steppable. If you want to do it by hand, you could just put in the step function, if not MCS percent 5, and that'll make it every 5. So let's use the pressure. Let's use the pressure using a tracking field. So let's add a tracking field for the pressure. And the tracking fields are put it's the only thing we ever do in the init. So this tracking field goes immediately after the steppable base pi init. So find that, and it can go anywhere. It doesn't have to be it can be in any steppable.
okay. We'll just go into the growth.
But the growth one would be a good place to do it. And then you add, again, find in the Python functions, it'll say auxiliary field, extra fields automatic tracking, and pick the scalar attribute one.
Okay. Yeah, I did that.
Okay.
Yeah.
And so now let's call this field name pressure. And the same for the attribute. And this reads the self dictionary. And so we have to do something that seems sort of silly, which is in the step function somewhere, after here would be fine. We have to copy, we have to say cell.dict pressure.
Wait, so that's really.
If you don't remember, if you go to cell at CC3D Python, cell attributes,
So
dictionary, or somewhere in there, there's a dictionary. Where is? Yeah, the first one.
Oh, it's just key of the function.
And that would be equal cell.pressure. It feels funny to have to copy it, but the plot will only plot the dictionary. So you're now get rid of one, get rid of those. Okay, good. Now run that. Save it.
So I just stop.
You'll have to stop and start.
Okay.
And now you're gonna take one of these and pull down cell field. You'll have pressure, display pressure, have it running now.
Oh.
No, don't hit stop though. No, what, create a new window. Okay, make that pressure. Okay, now run. Run. Don't, no,
okay.
Never, unless I say stop.
Oh, okay.
Don't stop.
Okay.
Okay, and so now you could see in the middle here, the pressure is negative because those cells are compressed.
It's all negative actually, but maybe here like 0 is.
Well, sure, because as the thing is growing, the actual volume is always going to be less than the target. But it's more negative at the center than it is at the edge. So you have a pressure gradient in the simulation. Now, the one thing that you have to be a little bit careful about is that by default, the tracking field will auto scale the colors, and that can be confusing sometimes.
What do you mean, like all scale? Like all scale by,
So blue will be the lowest value, red will be the highest value, whatever they are. And if the minimum and maximum are changing, the meaning of the color will be different at different times. In other words, if you look at this color bar here,
like this color.
the
is
minimum and the
changing.
maximum, the minimum value here will change
Oh, okay.
as time goes on. That may be what you want, but you might want to fix the color so that if yellow is the same at all times.
Oh, yeah, so you can see like spatial change.
Right, yeah.
Okay.
So let's just let it run another couple of steps till it runs into the edge.
Mhm.
And then you'll see the pressure will get large and negative everywhere.
I think it's really hard to with the sound of the camels.
Yeah, maybe, well, that's why originally I said to make a smaller simulation, so that it would run into the edge fast. But anyway, we'll just wait on, it's only.
Okay. I think that maybe like 10 years ago, 8 GB memory is already like a very huge memory for computers and now it's.
Yeah, it'll only. But you can see the pressure gradient really clearly across the cell, across the tumor, right? Right,
It's like a ring.
rings, yeah. Now, if we slowed down the growth, the difference between pressure in the center and the edge would not be as big. Because this is because the tumor doesn't have time to mechanically equilibrate. It's growing so fast that the stuff in the middle is growing so fast, it's pushing on the outside faster than the tumor cells can rearrange. That's not really biological. And there's some truth to it, but this is growing way too fast to be biologically realistic. Again, it's good that it's pretty small, but keep an eye on what the minimum and maximum values are. And get a sense of what the range is. It'll tell you here, it's also tiny what the min and max.
After it fills out the canvas and maximum, it became also like a negative value.
Yeah, and it'll keep going down. Once it runs out of medium. Yeah, if we only plotted here every 10 Monte Carlo steps, the whole thing would be much faster. That plot is what's that graph is what's slowing down.
So can we could just cancel this one?
No, you
Oh,
can't.
you want to see that?
No, but if you it won't like it if you kill that window. Then when it tries to write to the window, it'll complain.
I can just annotate this line.
Right, but then we have to start over.
Yeah.
Might as well just let it finish the.
Okay. I mean, like.
For next time, we'll start over.
Okay. Well, also, I noticed that like, I think the children.
Yeah.
Are like, does that mean like some cells are like they're really like compressed into very small volume?
That's right.
And they would not be able to.
They
actually
can't divide, that's right.
Okay.
So one game we could play would be, let's let this finish and then we'll do, is to have the cells divide not on the actual volume being double the original volume, but the target volume being double. Then they divide in synchrony. If you divide on the target volume instead of the actual volume, then they'll all stay in step with each other. The actual volumes will drift, but the division will be synchronous. Okay, so now almost one more round of division, I think, and we'll be the other thing that's happening here is actually the pressure is so big inside the middle that some cells are getting squeezed out of existence. They're being crushed. Which
That
is,
could happen, but there is sometimes some cells where disappear.
yeah, if you make the target, if you make lambda volume not big enough, the cells can disappear. Now, in reality, cells can be killed that way, but it's probably not biological. I mean, it means you're pushing the simulation too hard. It's not something that you want to have happen. All right, so I think we've got, well, there's still just a tiny bit of red in that bottom corner. How many cells are there now in the, it'll tell you in the console, it'll tell you how many.
Oh, here, I found it.
1,600.
Still
One red voxel left. So the next one it'll.
Why is there like we can see some red?
Well, remember, it's gonna adjust, so whatever the minimum value is will be.
But it's still like there are some places.
Probably because we killed the cell by crushing them. Yeah, so some cells are disappearing is what's happening.
So like the forest temporarily empty.
Well, actually, no, I think those have just happened to be the lowest. No, because if you look at the value there, it's not the same change.
But you can see like here, the max is still
Zero?
Yeah.
All right. I am puzzled. I'm not sure.
I think in this case, it only means like this little place doesn't have any sound
That's
here.
possible.
I think that's kind of interesting because like as I guess the cells are dividing, the number will be exponentially increasing, but if it's cell I have been like really confusing how to control the cell number, like the agent number. Because even like the cell I wanted to disappear. Where the necklaces were apoptosis, but they're still there.
Well, so no, you can make, if you want to kill a cell, the way to do that is to set the target volume to 0. But you have to also increase lambda volume to be a large number. Because remember, the volume constraint is not the only thing acting on the cell. And so if there's some other things that are trying to keep the cell there, and you make the lambda target volume 0, it doesn't automatically destroy the cell. You have to get the volume of the cell to 0. The moment the volume of the cell is 0, the cell disappears. All right, so I think, where's the plot? Let's look at our plot. There. So now what we should see is that the volumes basically don't do much anymore. They're distributed all over the place. But the target, the surface area should keep going up. It may be hard to see. Let's do a simple change to this, which is let's change the now we're going to I think we've got everything out of the simulation we can for the moment. Let's go back into the code. And let's make the cells divide, not when the volume becomes 50, but when the target volume becomes 50.
Um. what's the-
And that's in the cell mitosis step as well.
mitosis step.
So instead of cell dot volume, it would be target volume. Or capital V. Yeah. All right, and now,
So we just stop and restart, or
and
Do
then
you
the
want
only
to-
other thing I might do, no, actually, this has to, when we do that there, it has to be target volume. In the growth function, let's see, in the growth function,
Mhm.
the one thing I might do is make this, instead of cell dot target volume, make it cell dot volume. There. Okay, so try that. Let's see what happens. What do you think is going to be different now?
Wait. Um. So just leave here, still like target volume.
Well, because when you change the target volume there, the cell doesn't have time to change its actual volume. And so the step function will automatically do the thing you've done there. So
Mhm.
if we've divided the target volume of the parent by 2, but the actual volume of the parent isn't updated until later. And so if we're going to update the target surface, we can't do it based on the actual volume because the actual volume hasn't changed yet.
Mhm.
So we have to use target volume in that line.
Oh,
Okay, try hitting, so save that and try running that. And it's gonna actually, at the beginning, it's gonna look the same and it's gonna look different as the simulation goes. And let's turn off, well, no, we don't want to turn it off completely. No, we don't want to turn the plot off because we actually want to see, the plot will look quite different. So let's stop it and run it again. Now hit stop and run.
It reports error.
What did
So
it say?
G. Oh, I
What?
think I might have a typo here. Cell G object. Let me see which one.
Oh, because the volume isn't capitalized.
Oh,
Because it's Python, so capital V and small v are. So it's in
so
line.
I can't capitalize this.
Yeah,
Oh, actually,
those are different, yeah. So now everybody divides at the same time. Regardless of how big they actually are, they all divide synchronous. So this is actually going to grow faster because we're forcing the divisions to be every 10 Monte Carlo steps, no matter what. Now look at the pressure. Let's look at the pressure.
Right?
Look what happened.
I think it just crashed.
Why did it crash?
Sorry.
Hmm.
It crashed, sorry.
Relaunch player.
Yeah.
You shouldn't have to close Twit. It should be.
Oh, it's separate. Okay.
Sometimes when the Python kernel it kills player 2, but usually Twit will put it 2, but usually Twit will stay alive even if player crashes. The tracking fields sometimes have trouble with negative numbers. So it's possible that tracking field got upset because the values got to be 2. I don't know. It should be. Okay, so let's see if that's. Let's see the tracking field.
I might just open another.
Okay, that's fine. So, Okay, then you have to hit run after creating a window.
It's,
All right,
uh,
that looks okay. I don't know why. So again, some of what's happening there with the colors is because of the auto scaling of the color. But you see again, the pressure is high in the middle and lower on the surface.
mhm.
And
Why
now
is-
now they divide, no matter how big they are, they divide at the same time,
Mhm,
which is clearly not biologically right. That's,
mhm.
you could see the average cell volume is going down because they're dividing not when the actual volume is something, but when the target volume is. All right. So, all right. So, I think that's pretty good. So that, I mean, again, it'll take a little while to play with things, but I hope that, now there's something that Maciek did not want to add to CompuCell that I insisted that he do, and it doesn't work terribly well, which is at the moment when you do a print statement in the CompuCell, the print goes to the console,
Mhm.
but the Python console may not be easy to see. The Python console, you're supposed to be able to redirect it to the player console, but that doesn't work. For some reason, that doesn't work. There's actually an option to tell it to print to the window you're looking at right now. That doesn't work. So there's a function in CompuCell for displaying text. And that's in the start function, you could say add new message window. And that will pop up a little console window in player.
It's so like which start?
Anyone.
Okay.
But you only remember you're only going to have access to it in the, it's like all classes. So wherever you think you're going to be printing, put it in that one because you otherwise you have to do that game where you pass the functions between classes. So let's put it in the let's put it in the let's put it in the mitosis steppable. It's fine. This is mostly if you were going to be building a simulation that was going to be distributed for other people to use, then this would be nice because this, suppose you want to tell the person, please type the number, please enter a number in my simulation. Now, suppose you want to have some user interactivity and you want to give instructions to the user. The problem is at the moment, if you print, the print will go to the console, which they may not see. So this way you can make something display inside of player. So did you try this? Now try running that.
Try.
So now in the step function, you could just say self.message_win print steps equal quote comma MCS. We're not going to use this as often, but when you're debugging, it can be used. And you don't need to use the style.
Okay,
It's just giving you options for.
So just get the colors and.
Yeah, that's good. Okay, so let's try that. So now, did it crash?
I think it's just
Huh.
taking time to load.
No, what happened? Why did it not like that? Where did you put it?
I'm moving my
You
keys.
put it in the stat, yeah.
Wait, I think it's because I did this, I said here, so,
Wait a sec, where did you put the start? Where did you
I
put
put the
this?
star under growth double,
No, it has to be in the same step.
yeah, but I didn't have a star.
No, but not in the init, in the start.
Yep, so I have to
Oh,
create
you
a
have to create
star.
a start, okay. Same thing we had before with the growth thing,
Yep.
and then move the plot.
Well, I think that one, I have to restart that one, because that still.
Yeah, we killed the kernel on that one, I'm afraid.
I'm gonna just say this first.
Yeah.
So,
Okay.
this. I think we have to force it to.
Okay. There. Okay, so there. it is.
So, why it's not. Is it running? Oh,
Yeah, there it is.
okay.
Okay.
I'll see.
Yeah. Not very interesting, but if you need to communicate with a pop-up window, now you know how to do it.
Okay. So I think it's kind of like similar to the Visual Studio. Why it's really useful.
Well, Physicell Studio is a little bit easier to, I'd like this, I wish I could have all of these things predefined like Physicell Studio, where you just check a box and then it gives you the code. We're trying to extend Twit Wizard so that it does all of these things more with a GUI rather than having to make you type the code. Right. So I might comment out those lines that you just added for the text windows. They're not, I mean, I would comment out for the things we're going to keep doing, I would get rid of this. I would comment out the print message thing. In other words, I would disable what we just did. That one is not one we're going to keep using for the next. Having the message window available is good, but we don't print to it unless you need to. Okay.
But it can still like see this,
Yeah, in the console, in the general console, you always have everything. The other thing that I wanted to show you today was histograms. And there is in the Python code snippets, there's a line, scientific plots histograms. And creating a histogram is just like creating a plot, a regular plot. And what's something we might want to histogram? Well, we know that the cells have different volumes. We also know the cells have different pressures. So we might want to histogram the volume and the pressure.
yeah.
So let's think about how to do that. The commands are almost the same as for scatter plots. So you go into the start function. You go into the start function and you now put in, you select go to the Twit menu for scientific plots, histograms,
Mm.
and you put the initializer in.
See. So
Wherever you could put it after where you did your other plot windows. So just wherever you had your other plot windows, you could put it in.
start function. So
First, let's just do the start function first.
okay, I did that.
Okay, now we're gonna have to do a little bit of editing. Let's plot a histogram of well, the volume is okay, so we could have a volume one to begin with. So let's do the volume histogram. Typically, you don't overlay more than one histogram per plot. You can, but you don't.
So just you mean like delete the
Yeah, I would get rid of those
So-
two. Yeah. Those are more to show what you can do. Yeah. Okay. So let me just check. Okay, fine. That looks fine. And now in the step function, we have to create a list of the things we're going to plot. And this one, I put the pressure, but let's do the volume first. So let's create something we'll call, say, volume list in the step function. We'll create an empty list, volume list. And then we'll do for cell and self.cell list. And then we'll do volume list append cell.volume. And we can do the same thing for pressure in a minute, but let's do volume since that's what we started with. And then if we go into after we've created that list, we can do add histogram.
it should be like out
Not
of
inside of the loop, yeah, well, out of the loop.
and only like
And you only have
zero
one histogram to add, so you get rid of the ones you don't want.
and- yeah, and
So let's just take a look. So one thing is plot win, you'll have to change to something else like hist win here. Because
Oh.
you already had plot win, so those have to be unique, so.
so
And then you have to change it when you created up here,
Yeah, okay,
you have to
yeah.
make that unique. Good. And then plot name hist, we have to make that good, okay. And then value array, we have to make volume list.
so what is the bonus?
I have no idea, I don't know why I don't know where that came from. That seems like a really strange choice of default to me, but. And now let's try running that, see if it works. Oops, there's a type. We have a typo in somewhere where,
This one. Do you mean what? Do you mean
what line?
message one? No.
So what was the error?
This is like this. Hopefully, didn't have actually this one to the message one.
No, that's,
Mhm.
I don't know, those suggestions are terrible, I don't know, that's Python now is making weird suggestions, that's new.
So let me just annotate this. And what? Oh, I think it's because wait, you.
No, that's your regular ones, this is right. No, don't change that, no, no. No, that's the other one, that's the scientific plot, don't touch that. It's this here. Hist win here. Now we've got to go down. So not hist win. What is wrong? Somehow this syntax. This should be so, yeah. Let's try it again.
Okay. I still have.
I can't, you're going too fast for me,
I'm sorry.
sorry. Scroll back to the beginning, so why don't we make this bigger so we could see what's going. Okay, so the error is mitosis steppable object has no attribute hist_win. And then it says, scroll down, and what line is it having trouble? So hist_win add histogram plot is the problem. Why? Okay, so let's look in the code.
Maybe it's not,
Where did we put it, is the question.
here,
should-
I'm sure like they're only the same.
Yeah, well, if the plot, if the regular scientific plot works, then this one should work. For some reason,
But that one's let me use the place.
this, for some reason, 71, scroll down.
Mm.
Comment out line 94 for the moment. Let's just run. Now let's run. So it does. No,
I think
it's
this is,
dying, it's still dying even,
this is
what line?
line
71.
So
Where's 71?
when the hist was
So it's
first
not
pops up,
able to create it. Why is that?
is it because it's not defined in the like what's it called step pool?
I wonder if histograms are not available in mitosis. Pedro, are you still there? No, Pedro had to drop off. So I wonder if there's an issue. So let's do it. Huh.
I guess like if you change the hist one here,
No, that's not, this is a different plot. It's line 71 that's the problem. So go to line 72. And now let's go back to the pull down the CC3D Python.
Mm.
And go to scientific plots histograms, add histogram plot.
start from
Right.
here.
Okay. So why is,
The default is plot with
right, so all we changed was plot win to hist_win.
do you wanna try the plot with here?
Oh, wait a sec.
Mhm.
So you didn't create this oh, I see what, I'm sorry.
Mm.
So no, I misunderstood what you did. Yes, this has to be hist_win here in line 68. That's mine. I misunderstood what you were thinking. My
Do
mistake.
you like change here?
Okay, now get
Okay.
rid of, no, that's correct. Now put this, get rid of all this stuff we just pasted in line 73.
This is weird.
Now it should be. I misunderstood what you were doing. Okay, that should be fine. Now it should.
So let's just
Now
cancel
put it back.
that one.
Okay, sorry about that.
Oh, it's still good. It's so good. Oh,
There it is.
that's really nice.
Now, we only have 10 bins and we're updating too frequently. We probably shouldn't update it as frequently as that, but it's so you get the distribution of the
Volume.
volumes. Now let's do the pressures too. Let's add another histogram with the pressures.
Oh, let's just like pause this simulation.
So
Mhm.
we'll have to do both. We'll have to do line 68 again, because we don't want them on the same one, so we'll have to do. Copy those and call it, say hist_win2, which it has to be a different window. And this will be histogram of cell pressures.
Do you Do you have to like change the title?
Yes,
Okay.
that has to be in
Oh,
the,
it's pressure, okay.
that's
It's volume, so the pressure.
supposed to say
Yeah.
pressure. The other one doesn't matter. The title for some reason actually matters, but the,
Oh, okay.
and then that'll be history 2, and then the other stuff can be the same. Well, it's 2, sure. And now,
Oh, should we like copy, like also like create a list and.
yeah, you could do them both in one loop though, so you could, so,
Oh,
so
yeah.
copy line 100 and paste it in. And then make it history 2 and then make it pressure. His2 pressure. It'll be pressure now. Pressure list. And then this will have to be win here where you have win, it'll have to be win 2, line
Oh,
102.
And
Okay, now we need that pressure list. And then we can do the same append that we have with.
This.
Pressure list. Pressure, SS, yeah, okay, that's depends on that pressure. Okay, okay, see if that works.
Pressure. And volume. Oh, it's like.
It's updating too fast, huh?
Let's see.
So we might want to update those every 10 Monte Carlo steps instead of every Monte Carlo step. So let's go here, let's go in here. And put all of this line 97 to 104. Put a if not MCS %10. If not, parenthesis MCS %10 colon. And then to do it, then select all these lines and then hit no over here, that one. Tab will work too. Unsave. Now it won't update so frequently, so let's get back.
Wait, but another thing that I noticed
Yeah.
that they show like exactly.
Oh, they're the same? That's not good. So something,
It's actually not same. The X is not the same. Let me go back to the code. Boundary pressure list. Oh, it's.
no, it looks right.
It's right. Pressure.
Huh, okay. Well, let's see if they stay the same when it keeps running. It may just, I
Okay.
have a think I know why it's that, but let's see.
Still like that way.
Oh, it's because we better go back to dividing on actual volume, not on target volume.
Oh.
That's
Okay.
that's what's causing the problem.
So you.
Just volume. Lowercase, yeah. Everything else should be okay.
Yep, thanks. I didn't change anything else.
That's right. That should be fine. Now let's try it.
Are they different now?
Yeah.
Still.
Yeah. No, they're different.
Yep.
So now let's let it run for a while and see what we get.
But why did the number of cells like connected number?
Oh, because it's not really the number of cells, it's the pressure. The x-axis is the pressure.
Oh, so.
We just labeled it wrong.
Okay.
So the x-axis should be volume and number and pressure rather than.
Oh, it's actually like a distribution plot.
Right.
So
right.
like the y-axis is
the number of cells, yeah.
Okay.
So we got it labeled wrong, but it's okay.
Let me go check. Oh yeah, here like because
So the histogram of pressure, x-axis should be pressure,
Yeah,
and y should be the number of cells.
let's see.
And now if you turned off that plot of all the cells. So one thing we could do is instead of plotting, something I would do now, and maybe it's a tiny exercise, but take a minute. Instead of plotting every cell's volume and surface, I'd calculate the average and plot the average versus time. Because you don't need to see it's not really meaningful to plot. The histogram is interesting, but the other one isn't so interesting. So where you calculate
Like to calculate the average volume.
right, yeah,
So we just find where did I put this?
it's there, just above line 57 and 58.
Oh, okay.
But now you'll have to create a placeholder for the average volume and the average surface.
Do you want me to?
Move that out of the loop.
Oh,
So I want you to figure out how to calculate the average volume of the average surface.
and sound them together
No, just separately.
separate.
Well, sorry, you mean how do you do that?
Yeah, I need to
Okay,
calculate it.
so inside the loop,
Uh-huh.
so before the loop, create a dummy thing, which is total
Yeah.
volume and total surface.
To the volume
Yeah,
and to the surface,
right,
okay.
right.
Surface.
Don't use a minus sign.
Yeah.
And you probably want that to be a float, not an init. 0.0.
Okay.
Okay. And now you can add to those two the actual cell volume and surface.
Total
Surface, yeah. Volume, yeah, and the same thing for surface.
And then after remove, you just
Now you have to divide by the number of cells, though.
average. So you just create two new variables.
So to get the number of cells,
Wait, how do you get the number of cells?
so you could add one, you could have a counter there, but the easiest way to get the number of cells is, let's say, n cells. It should be it should be something there should be self.number of cells,
Yeah.
but there isn't. There isn't. No.
Okay.
So do self.n cells equals len, L-E-N, length,
Oh,
parenthesis, self.cell list.
Okay. But that's a quite simple version though.
It should be there. There should be self.number of cells, I agree.
Average surface
Oh.
Equals total surface divide n cells.
And I guess if you're being careful, you probably should have an if statement to make sure n cells isn't 0.
Oh, yeah. So
After that, you should say if.
and so
Greater than 0. Not equal 0, but okay. And then those are fine. And then, yeah. And then we have to change lines. Okay. You have to change what you're plotting.
So it's not.
Now it's just
an
average, so
attribute,
yeah, it's
though.
not an
This is volume.
And that'll also run faster because we're not gonna have so many points. Okay,
Did I remember?
I think that looks okay. I'd indent that because that should be inside your if statement. Because if there's no end cells, then those variables won't be there. Fine. Okay, good. So let's see if that works. Let's look at this plot here too. Yeah, so now that's
Yeah,
behaving. So now everything is behaving pretty well. The only thing is the cells are growing too fast. Look how much faster it's running.
yeah, so
That plot was taking a lot of time.
so you want to change it back to 25.
Yeah.
Okay.
It's sort of strange. The print statement in Python is really slow. Just print is really slow.
Oh,
You'd think print should take no time at all. It's slow. And the scientific plots, if you have a lot of points, because it looks like it's continuously updating the screen, but it's actually blanking it and redrawing the whole thing every time. So so when you have too many points in the plot, it takes so long. So now you really have a pretty good simulation that you could use to do things. Now if you had a cell cycle model, you could put it inside of this. You know where it goes, right? Oh well, I take my very simple rule. I take my very simple rule for cell division, and I put in a more complicated rule. But it doesn't change the structure of the code. It's just the line if cell dot volume greater than 50 is replaced by your more complicated rule. So actually you've done quite a bit here. Something that may or may not work in your simulations. If you go to the plot windows, then you right click on the plot windows. If you right click on the plot window here, and just hover over that and right click on it.
Oh.
And you hit export. You should actually be able, don't do it because it may crash, but you should be able to actually save the image and also save the data. Yeah, if you export it you could export it as a
I didn't see there's a. Oh, you mean the CSV?
CSV, yeah. So it'll actually export the data. You could do that from inside the simulation, but if you forgot to do that, you can by hand save the data set while the simulation is running. Now, some of the options that it gives you crash the system, so I can't promise they all work, but that's pretty nice that you could do that. So we already did the fixed volume one. Another thing that's sort of interesting is if you have the cell division not be random, but be oriented. So that's a game we can play. That's sort of fun. Try that, maybe. Try the divide cell orientation vector-based one. See if it looks different.
Dot be 110 vector.
No, it's fine. The direction doesn't matter as long as there's some direction.
I think it takes a while. So it's been.
Yeah. Since the cells rearrange a lot,
But you
you don't see it much because this thing rounds up.
you can already see like the
110. You can see the axis, yeah. They all divide along the same.
Yeah.
So it's getting stretched that way. So that one you can do. And a more interesting thing is we know in reality that cells have a contact inhibition of growth. So there's a biological process called contact inhibition of growth. And so in that case, when cells are in contact with each other, they send a signal that says, don't grow, stop dividing. And so it's not a great surrogate for real growth, but you can define a hill function. Again, we should have the hill functions predefined. I think they may even be predefined, but I don't remember what they're called. We should look, because I think I asked Maciek to add those. So what you can do is you could say, okay, now I could say, instead of having the growth rate just be constant, I say if the pressure is too big, the cell doesn't grow. And so now I multiply that growth rate by a hill function of the pressure. And in that case, you should see the pressure stays pretty uniform.
Oh, because like once the pressure increase and they just
They don't grow
yeah,
anymore,
they grow like
slower,
lower,
right.
so it's just like kind of like
It balances.
yeah, maybe.
And that's pretty realistic. I mean, again, in some cancers, they don't respect that signal very well. But even in most cancers, the cells, if they're under too much pressure, they don't grow so much. And so of course, we could also have nutrients, we could have growth factors. And so the next thing we'll do next week, we'll do chemical fields, so we can have the cells take up the chemical. We'll start out with just something where we say, imagine there's glucose, and the cells take up glucose and turn it into mass. So the growth rate will depend on the glucose availability. But again, once you've done that for one chemical field, well, you've already done it for your bacteria. You have it for 50 20 chemical or 30 chemical fields. Once you do it for one, once you know how to do it for one of them, you can do it for all of them. And then the other thing we can do, which will be another week or two before we get to, is you can suppose you actually had an explicit cell cycle model inside of the cells. I don't know, maybe, do you know the Tyson model of cell cycle? There's a famous model by John Tyson of Virginia Tech, of a simple model of the cyclins that control cell division in eukaryotic cells.
I'm not familiar with the name.
But we could take one of his models of cell division and then run that inside each cell to control the cell division, for example. And that model takes you between G, S, G2, M phase. Yeah, that model will take you through those phases. Of course, it runs a little slower because you have a more elaborate model inside of each cell, but it's not bad. It runs pretty fast. Another thing that happens in some mammalian systems is there's a contact signaling mechanism called delta notch, and that also affects the rate of cell growth. And so that can be included. Or you could have a growth factor. Do you have endothelial growth factor or the vascular endothelial growth factor, that the growth depends on the availability of a growth factor in the environment too? Because in tumors, you have a little bit like your substrate exchange in your bacteria. The tumor sends out a growth factor that makes the blood vessels grow, and the blood vessels send out glucose that allow the tumor to grow. So they are exchanging growth signals between them. So that happens in a tumor as well. I guess we're almost out of time for today, but the next exercise I would say, and maybe we'll have this as a homework, we can start out with we could create a new cell type, which we could call quiescent, for example. And then, well, in this case, we just say that the cells become quiescent and the quiescent cells don't grow. That's maybe not the most interesting exercise. But in that case, only the initial cell is proliferating and it just keeps, so then you have one cell growing and dividing instead of all the cells. That's not the most exciting model, but we could do that. But the one that I was talking about was this one, where you say, okay, we define a function of the pressure, and you'll have to look at the actual pressure to say what the range of the pressure should be, because you have to look and see what that actual range is from the plot. And you'll say, okay, if the pressure is too big, then the growth rate goes to 0. And you could do either a linear decrease of growth, or you could do a Michaelis decrease of growth, or a Hill decrease of growth. And if you use the Hill function like this, or the linear one works too, because in this one, if the cell gets under too much pressure, it actually shrinks a little bit, because it could go negative, right? This one can go negative. But this, if you use a Hill function like this, it actually, you'll get pretty realistic growth patterns. You won't get this huge pressure in the middle of the tumor. And so you can play with that. If you do the linear one, then the final pressure will be whatever you set P reference to be here. It'll adjust so that the pressure everywhere is just whatever the target was for the linear one. And that's what I had planned for today. We got through a lot of material today. I hope it was clear.
Yeah.
Do you have any questions or things you want to talk about today before we break for today?
I don't have questions, but I have questions about like how we like assign time to talk about the assignments. Because you sent me emails saying that I could leave some questions to talk.
Right. Well, if you want to go over things now, that's okay. I can stay for another half hour if you want to go longer. If you need to go home, that's okay too, and then we can make an appointment later in the week to meet. You tell me what's better.
I think we're just leaving an appointment.
Okay. You want to try to do that now? Let me pull up my calendar and let's make an appointment.
Yeah.